Alrighty, so can everyone hear me?
Yep.
Oh, great. Well, let me go get this started then. Share screen and screen one. Great. Switch up. All right, great then. Well, hello there. Welcome to the virtual lesson. This will be fast-paced, and this is to programming with VRS. If you have any questions, feel free to go and put them in the chat. I'll be sure to answer them when it's appropriate. And there's a good stopping point. And let's get on with it. So here is what we will be covering today. First, we'll go over what FTC is. Then we'll go over the basic bits of VRS and how to set up the coding environment and experiment with the virtual robot simulator. Third, we will learn how to program basic block movement commands with blocks. And then fourth, we'll be able to apply that to Java to then learn how to code some basic things in Java, specifically on bot Java. And for the fifth, you get to know, you learn a little bit about who we are, which is quality control. So first is what is First Tech Challenge? Well, First Tech Challenge, or FTC simply, is a robotics competition for students in grades 7 to 12. The object in it, teams design, build, and program robots to compete in an alliance format against other teams. The competition is designed to help students develop STEM skills, problem-solving abilities, and teamwork skills. There are also 3 other partner programs for those who are interested in pursuing FTC, but want to do it at either a more advanced level or at a less advanced level. For those who are more specifically in high school, FRC, or First Robotics Competition, is recommended. And for those who are in middle school or below, FLL is recommended, which is First Lego League. And they're all partner organizations of FTC. So, to get you an idea of what FTC is like, let me show you a video of this year's game.
A team consists of up to 2 driver operators, a human player, a coach, and a robot. Each match is played with 4 randomly selected teams, 2 per alliance. But each alliance is allowed 1 human player. Your opponent for 1 match may be your partner for another. Robots must be built from materials specified in the competition manual and fit within an 18-inch sizing cube. But after the match starts, robots may expand, but may never horizontally exceed a 20 by 42-inch rectangle. The primary scoring element is a plastic sample, 1.5 square by 3.5 long. There are 20 samples for the Red Alliance, 20 for the Blue Alliance, and 40 Yellow Alliance neutral samples. Another game element is the clip. Each alliance has access to 20 clips. Human players may attach clips onto samples to create specimens. The game is played on a 12-foot square playing field with a foam tile floor and 1-foot-high walls. A submersible structure is located in the center. Within the submersible are the barriers, low rungs, high rungs, low chambers, and high chambers. In the opposite corners are low and high baskets. Below the baskets are the taped-off net zones. On the other corners are taped-off observation zones. On both sides of the submersible are the ascent zones. Near the front and back walls are the taped-off red, blue, and alliance neutral preset sample zones. April tags are located on the field walls to aid navigation. Blue and red alliance areas are on the left and right sides of the field. Before each match, 60 samples are randomly arranged in the submersible zone. 20 clips are positioned outside of each observation zone, and 12 samples are positioned on the preset sample zones. Teams place their robots on the field, touching the sidewalls. Each robot can start the match with either 1 specimen or 1 sample. The field and players are now ready. The match begins with a 30-second autonomous period. During auto, robots may attempt to score using pre-programmed instructions and sensor inputs. Following auto is the 2-minute teleoperated period. Robots score using driver inputs. There are many ways to score during the auto and teleop periods. For example, scoring a sample into the net zone earns 2 points, and scoring a sample into the low basket earns 4 points, or 8 points for scoring into the high basket. Robots may bring alliance-specific samples to the observation zone. Human players can attach clips to the samples, turning them into specimens. Scoring a specimen on the low chamber earns 6 points, or 10 points if scored on the high chamber. Sample colors may be neutral or alliance-specific, but specimen colors must be alliance-specific. The last 30 seconds of the teleop period is the endgame. Robots may continue scoring, but have protected access to their ascent zones. Each robot contacting the low rung earns 3 points. If a robot achieves a low-level ascent, it earns 15 points. But a high-level ascent earns 30 points. When the match ends, a robot parked in the observation zone earns 3 points. There are many ways to score in Into the Deep, but there are also rules that, if not followed, will result in foul points being added to the opposing alliance's score. A robot cannot enter the observation zone if a human player is in that zone. Scoring elements may not be launched. During endgame, robots may not interfere with other robots in their alliance's ascent zone. This has been a summary of this season's game, Into the Deep, presented by RTX. For complete rules, please read the competition manual and check the Q&A forum. And always remember the most important rule of the first tech challenge: gracious professionalism. Good luck, teams, and have a spectacular season.
Well, that's the FTC game for the year. If anyone is, again, I highly recommend joining FTC if you are interested in pursuing robotics, or more generally learning some very useful STEM skills such as programming, 3D modeling, and CAD, which have become increasingly valuable resources in today's ever technical economy. So I posted a link to the FTC website if you would like to check it out, and if you would like to form a team with some friends of yours or some classmates or whatever. Again, I would highly encourage it, and you can really reach out to my team, Team 2229 Quality Control, or really any other of the experienced teams out here in Washington. We provide real great support to help mentor and to help foster new and upcoming teams, so that they too can be able to develop the field of FTC and be able to make it a real great place. So now on to the okay. So now on to the next part. So what is the virtual robot simulator? Well, in short, the virtual robot simulator is a platform that allows students to program and test first tech challenge robots without the need for physical software. The VRS was made in the collaboration of veteran FTC members from across the U.S., including myself, Nishant from Quality Control, and a lot of other wonderful people that I've met along the way. For those who are interested in the website, I will post it in the chat again. Here you can go and access all the previous VRS. Let me just screenshot this perhaps if you share this. So you can see the you can see the virtual robot simulator screen, yes? I'm sorry.
But you, it's a dumpster.
I'm sorry.
Yes,
Sorry.
we can see it.
Oh, great. Thank you very much. Well, here is the virtual robot simulator website. Again, they provide a lot of great tools for new and upcoming students. Here, there's a setup installation guide, and there is also a guidebook, which I helped develop and wrote. And this basically will help you have all the basic information you need to be able to use the VRS and provide a lot of useful tips for more generally if you do plan on doing FTC and program robots using that. And again, feel great to check it out. We've reached out 32,000 people, and this is where you can access the VRS launchers and get VRS. We have a lot of different simulators for each and different FTC game, but for now we'll be focusing in Ultimate Goal. So I'll post a link over to the chat. Oh, VRS simulator. So again, if you want to follow along, please go to the chat and click the link for VRS Simulator. That will be able to show you to the VRS website. So now let's begin with the first of this. So block programming. Well, what is block programming? Block is a visual programming language that uses interlocking blocks in order to help represent code. I like to lead off with this because it's very easy for beginners to pick up. The use of blocks help prevent syntax errors such as capitalization, using semicolons, and all of that messiness. And also it also helps visually represent the code so that it makes it real easy to understand what the code is trying to mean. So let's go with the first set of commands that you need to know. These is just the most basic things. So obviously the most important part of a robot, and I think that really makes it a robot, is that it can move. And how it does this is that it moves it through motors. By default, the Virtual Robot Simulator robot has 4 motors on the drivetrain that each control a wheel. These wheels are mechanism wheels, which will be important later on in the PowerPoint. These motors can only be moved by being powered. There's not some type of, move 5 meters or go back 1 inch or go forward 1 inch. Instead, it only intakes power commands, and there's no way of and unless if you have encoders, which we will not be using in this lesson, you cannot make it turn a certain distance otherwise. So here, let me explain how the motor block works. So in the most basic block, there will be 2 different sections that you really need to fiddle around with. The first is this first after set, and this determines what motor power is being set. In this case, front left will refer to this wheel, as you can see in the image. But the other wheels are labeled as you expect. This is back left, this is front right, this is back right. And then after that is setting, and then this determines its power setting, which is being set to this integer. And for now, you don't have to mess around too much with it. You just need to know that this is an input box and that you can type into it, which I will be doing in the person throughout this presentation. And this will let you control the power that's being sent to the wheel. So the power of this motor ranges between -1 and 1. The greater the magnitude, which is closer to 1 or -1, basically the further away from 0 it is, the faster the motor will turn. A power of 0 will naturally stop the motor. And positive values mean that the robot is moving forward, and negative values mean that the robot is moving backwards. Now, there are ways to go and reverse the motor direction, because when you install these motors, the motors may not necessarily be turning the correct direction the first time. So I will be going over that in the code about what we do in the event that the motor direction 1, because again, the rotors are not naturally aligned to the robot, how to go and fix that in programming. So first, go to the home page, which I recommended you to do. And let me share the screen. All right. So here, I hope you can see the screen. So first, hover over lesson challenges and click play. Then select level 1. Now, if you want to learn more in this upper right-hand corner in how to use, you can click it and it says, welcome to the Virtual Robot Simulator. It'll provide video and text guides. And, but, I'll be teaching you here. So, here, let me go explain to you how this works. So, the basic objective of level 1 is pretty simple. You move this robot over from here over to the flag. Now, there will be some preloaded code, but I'll teach you how to modify it. So, let's go over first how this code works, and I'll just program it by and now let's go analyze it. And when it needs to be modified, I'll go and modify it. So for now, this purple block will be the most essential part that you always need to have. This is the run op mode, and this is what the actual main program will be when you run the code. It is effectively a container, and although this doesn't actually do anything by itself, it just gives instructions to the robot to determine how it initialization. What initialization is that, as I was saying previously, the motors may not necessarily be aligned towards the direction of the robot. And this makes it kind of confusing because you don't want to make it so that when you're programming this, you have the right side have to be negative values to move forward and the left side to be positive values to move forward, or vice versa. It makes it very difficult on the programmer's perspective. It's much easier if you can just simply say, hey, I want all the motors to move forward. What do? I set all their powers to 1, the robot moves forward. It makes it a lot easier, and you can also then use variables to set the power of all the motors simultaneously without having to manually type in a bunch of values. So in order to achieve that, we use this set front right direction, and and for our purposes, since the right side of the robot is reversed, we set the direction to reverse, and then we call the program to start. So what this wait for start does is that when you initialize the program, there will be an initialization function where presumably the autonomous would occur, which is why there's a countdown going down. But and then afterwards, this wait for start is referring to the start program, where if you click it, the robot will move, and since there's no programming so far, it instantly ends. Now, this part is not necessary. Now, so when controlling motors, here is where you can find the motors. It's in this left side called where you can get all the blocks from. In this part, you go to a section called actuators, DC motor, and you can set the power of the motors individually by using these single commands, but to make things easier, there are quad commands, quad blocks, which set the power of several different motors all at once, so that it becomes much easier for you to just simply have them all in one chunk instead of having to set, for example, going around and just dragging set power, etc. You get the point. So what this will do is that this will set the power of each of these four wheels to 1, and since we previously reversed the direction, the robot will now move forward. If I go start. Oh yeah, and you may realize why the robot didn't just immediately move. Well, the reason why that doesn't occur is because you also need to sleep the program. Because what's happening in the program is that it runs these programs from top to bottom. What it does is that it goes forward, sets the directions, waits for start, you start the program, it runs this program, sets the power, and then immediately ends itself. And when it immediately ends, the robot just stops moving. So obviously the robot will not move. What you need to do instead is that you need to give it some time to move. This is what this program called the sleep program does. Now, what this does is that when you sleep it, say at default, it will run, at default, it is going to be 1,000 seconds, and this is broken in milliseconds, so keep in mind, 1,000 milliseconds of the sleep function is only equal to 1 second, so yeah, so keep that in mind when you're new units. And then you can see now it will successfully move forward for a period of 1 second before stopping. Now you notice that this may fall short in the program. So as a result, what we need to do now is, first of all, in order to get your robot back to where it originally is, click reset field, and this will let you to reset the robot. Is that you should extend the time by which the robot sleeps to, and for our purposes, it's been required to be 1.8 seconds, but obviously in reality, you will have to test several different values before you can find a good sleeping time. So then you start the program, and then the robot will automatically go there and move the flag up. Now I got recommended, now it's recommended to also, at the end of this program, although it works now, to set the power off of all of these motors. And by doing that, you, again, as aforementioned, you set the power to 0. This way, for safety purposes, it turns the power off so that when this sleep program ends, the robot doesn't just continue to just do whatever. This is more just a general guideline, since obviously when the sleep program ends, the program will end, so the robot will stop moving regardless. But when you are doing this for real, it is very important for safety that you turn the power off always, because you never know when you write some program and then the power doesn't turn off on the motor and then the whole robot gets broken and whatnot. It's all very messy. So that's it for the first lesson. And as you can see, we go there, we initialize the program, we start the program, it goes forward, and then it clicks on the flag. Pretty basic, right? Well, there's a lot you can do with even the most basic move command. So going back to the PowerPoint, we have a concept called strafing. And using those mechanism wheels I was mentioning earlier, if you use this can allow the robot to go in these types of specific directions as indicated by the chart. Basically, how it works is that these mechanism wheels have small rollers on the side of them, as can be indicated by the little dash marks. These little dash marks help to go in when they are rotating in certain directions, such as, for example, this one, where this is rotating forward, backwards, and forwards. These X shape will ultimately cancel out to help create a net force that will move the robot towards the right. And this is very special because when strafing, the robot doesn't need to, like, say, turn 90 degrees and then simply move forward that way. Instead, whilst looking forward still, it will move to the right. And this is a very useful thing in FTC because it allows you to go make a much more complicated movements in autonomous and in driver control, allowing for much better control of your robot. So now let's see how we can apply this. So going back to simulation, let's see here. Going back to simulation, we can go back and let's go to level 2. So now we can see that this is special. Now there is going to be a bend in the road. Now, there are 2 approaches to do this, which I will briefly touch upon. And that is, you can go forward, you can turn, and then you can go forward again. Or you can go and strafe. So for now, let me go over the first option, which is going to be the simplest to program. So once again, be sure to go in reverse directions of the 2 motors when initializing. Again, this code that pops up here is the same every single time. So it makes it easier for you because you don't have to recode everything the whole time. So for now, let's move. So now let's get back to where we originally were. So AC motor, quad. So this is the code where we were previously at. As you can see, we go forward. Yeah, that's it. So the robot doesn't really exactly meet expectations. And as you can see, even went slightly over unlike last time. So we would so you need to adjust the timings on how much you want this to move forward by. And after you stop it, you then need to do, you can then turn the robot. So how turning it works is that if you set the power to, say, set only this left side, turn off the power of the left side, the right side will naturally continue to move forward, and this will naturally rotate the robot. So if you just set the power over to 0 and sleep that for some time. I believe it should be around 300. We can go see the robot. Before, it's not nearly enough time. It seem. let's- And huh. That's well, that's not expected. So well, let's see what's wrong here. So front right, front left. Oh, I see what's wrong. So what's happening is that I'm accidentally I'm not saying the correct left side. So that my bad. Okay, I'm not saying the left side. So what's happening is I accidentally set the front left and front right together. So the forces are just canceling out and nothing is happening. So whoops. Okay, no, yep, okay, now it works. Okay, okay. We're getting for perhaps a bit too long. Go back. Back to program. And of course, you need to fill around with these numbers a bit. But again, now it turns roughly to the right. Afterwards, you just need to repeat the first part of your code, which is to move it forward by another 1500 seconds and then sleep it. And again, although not necessary, set the power over to 0. Reset the field, start, goes forward, turns right, and then, hey, look, it then moves the flag up. Great. So now obviously this is a little boring. What about if we use that cool method we talked about earlier? So we reset the field, and now you can see instead of having to go forward, wait for it to turn, blah, 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 what if we just simply got rid of this program, got rid of this bit, and just simply decided to just strafe it? So going back to what I said earlier, in order to strafe the robot, now the robot would need to strafe logically left. So I don't recommend you go and try to calculate these values by hand. It gets kind of complicated. So honestly, I recommend you just simply go online and Google up an actual chart of how the strafing mechanism works, because it makes your life a whole lot easier. So these are the values, I believe. Let's see, and I believe these are the values. So you go forward, you start the program, it goes forward that amount, and now you can see it magically will just move to the left. Didn't move to the left enough, but here, you see now it goes forward and now magically moves this way. Now, of course, when you really do this with an actual robot, it won't move as smoothly, but this is a basic idea of how strafing works. Now, on to the next concept. So, let's see here, share. So, afterwards, here's level 2. So now, let's go on to level 3. This is going to be more complicated, but this is just basically combining what we have already learned into a more complicated activity. So, going back to the previous screen. And again, if you're not following or if you need any questions, feel free to ask. But I entrust that hopefully you're all following. So here you go. So now, give it a second. Takes a while to load. In the meantime, we can just go in and get that code back to where we previously were. Actuator, DC motor. And again, if you have any questions, feel free to ask. So as you can see now, there is a U-shaped turn there is now a U-shaped turn. Now, we already learned how the turning solution works. It's all very boring and not very fancy. So again, I'm going to go with strafing for this one because we're generally speaking, when you do this in a real game, it'll be a lot quicker than having to go forward and rotate the robot and move back. And also, personally, for me, it looks a lot cooler. Obviously, you can't really do this with a standard car or anything like that. So personally, if you entertain me, let me just go over the strafing option first. So going back to where we are, we go this, front left, front right. Great. And So again, this is where we previously were. Go forward. Now, obviously the dimensions change, so you need to go and change how much you're running it forward by. But yeah, in general, here you can go forward, and now you go back. Yep. Hope everyone's following. Just here, and if you want to strafe to the left, you go -1 front to right, front right, and 1, back left 1, back right, -1. And if you want to go and strafe the other direction, which is downwards, you can. It's just 1, -1, -1, 1. So now what do we do from here? Well, we can go use that power function I mentioned earlier and reverse the motors. So how power works is that as an actual motor, it works it's a little complicated to explain because it requires a lot of physics and whatnot. But for what the purposes you need to know is that a positive power, what it will, is that due to how the electrical currents work and how it flows through the motor, it'll spin it clockwise, I believe. And if you spin it the other way, it spins counterclockwise. And what that does is that yeah, let's see here. Is it correct? So you just go forward, you spin, it spins counterclockwise. Yeah. So what happens is that if you spin it, if you apply the current in reverse, it will simply spin the robot backwards. Spin the motor backwards. And this allows you to do things like this, where you can simply set the power in reverse, reset the field, initialize the program, go forward, go there, and now the robot can moonwalk to the objective. No, not enough time, but here. 2000, that should be enough. Now look, go forward, and seems to do that for nearly enough time. Set the field. And again, when you're really doing this debugging, it's a very much of a pain for programmers. But you can go back and then goes all the way towards the back, moonwalks towards the objective, and raises the flag. Great. And that's how it works. If you want to see the turning solution, I can do that. I don't know if you want to or not. If you want in the chat, then please say so. But for now, I'll just continue on doing the rest of the lesson since again, if you do want the turning solution, be sure to tell me, or be sure to check out again the website or the PowerPoint because it contains the other solutions for this. So Java programming. So now we moved away. So now let's move away from the blocks code. Although it works really well to teach people how to program this, it slowly falls apart though when it comes to more complicated code. And when you do this for real, assuming you want to do this in an industry application, or if you want to do this in robotics, because blocks is obviously a lot of very serious limitations, such as the fact that it can only run one stream of code. It can't run parallel, or it can't run extremely complicated mathematical operations, and also more importantly, it doesn't have a lot of support. And this is why FTC has something called on-bot Java, which is just basically Java for robots. And why they use Java? Well, Java is a very versatile language in computer science. It's used for data sciences, machine learning, app development, and web development. It has a lot of libraries for different purposes. And more importantly, it's used to go and program the robots in FTC. And again, almost every single industry uses Java, so you definitely won't regret using it, including a lot of non-technical jobs that you may not assume uses programming a lot these days, such as the arts, for example, or in I think music remixing and whatnot. So now I understand that Java may seem somewhat complicated at first. You go into it and yeah, it seems a little nebulous. So I want to show you just how similar it really is to the blocks. So here we go back to level selector. Let's go back to level 1. So let's see here. Wait a second to load. And also just for the comparison, and also just to make comparison easier, I'll open up a second one so that you can really see how similar they are. So hello? Did I cut out? Um, can you see the screen? I want to be sure it appears as if I cut out or something like that. Anyways, so let's see here. So this is going back to the previous example. This is just the first one, and for the purposes of simplicity, makes it easy to understand what's actually going on here. So this is the first code we do in this lesson, just a couple of minutes ago. Go forward, blah, 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 goes forward, runs the code, zooms forward, hits the flag, raises it. Great. So now, when you go to Java, this will become a little nebulous. So keep in mind with me here, and let me just go and copy and paste the code since it will get a little long. I will also go and post this in the chat if you want to. Let's see here. Chat. Oh, well, apparently hits the character limit. Well, and as you can just see it from here. It's also in the PowerPoint, again, if you want to take a look at it. But so here we can see that this obviously doesn't really make a whole lot of sense, obviously. Like, this seems pretty complicated, seems pretty, share it in a document. Okay, sure, let me see if that's possible. Alrighty, so let's see here. So I just really quickly created a Google document. If you want to copy and paste the code, just go to that Google Doc. If it doesn't work, please tell me because I'm just creating this at the moment. But yeah, I hope you can access it. So alrighty, back to the presentation. So you get okay, it's in the chat if you want to take a look at if you want to copy and paste the actual code. But for now, just to make things easy, I'll just go let me go over what parts of the code is similar and what's not similar so you can really see just how really Java is just an extension of what you previously learned from blocks. It's not really as complicated as it initially may appear. So first, one of the more important parts of Java is that these are all the packages and what imports it needs to do. For now, you don't really need to care about these things, but these are all the basic things you need to import because the Java is not pre-built with the the motor code in mind. So these packages allow you to just easily implement it, which is one of the big advantages of Java is that it's very flexible. You can easily use this to do a lot of other things as well, not just for programming. So what you see here is that when you go in and when you do this in block programming, you get these 4 different motors: front left, front right, back left, back right. Well, you don't really get that in Java. Instead, what you have to do is that you need to create something called a hardware map. So what you do is that you have to define each of these different variables: front right, front left, back right, back left. And again, these are variables. These are just names. And what you do is that this is equal to hardware map, which has to be imported from the packages, and then you get the class, the DC motor, which is what these types of motors attached to the robot are, and then this is the name of the motor within it, and this is again set up within a more complicated thing. If you do actual FTC, you will have the option to go and change the names of these DC motor classes by in setting up the motor and configuring it differently. But for the purposes of the simulation to make things easy, it's named what it's named. So it's named what it is. So that makes it a lot easier to program with. And these names don't actually have any bearing on the on how the program runs. It's just a name for the purposes of coding. So now we can start seeing some of the more similarities. So in the initialization function I mentioned, where before you run any of the code, you reverse the direction of these motors. Well, we do something pretty similar to that here, where we do front right instead of set front right dot direction. We instead do front right dot set direction. So this is the actual command for the motor. And then we go into this, and then we copy and paste this, but this basically tells it to go in reverse. Same thing for back right. So you can see that these two are pretty much exactly identical. And then we go wait, and then we do this wait for start. And this is the exact same wait for start here as call program wait for start. Now after this is if call program op mode is active. This is not exact. This is more important if you do a real coding, since this is important for pacing the programs during the actual matches. But for the purposes of the simulation, at least for some code this simple, it doesn't really play a major impact. But this is basically the if statement. If the op mode is active, is the exact same one here. And then we can set the power of the motors. And then as we see here, we get no fancy quad block option, unfortunately. Java is not up to date in that respect. So you have to simply copy and paste the program 4 different times, or they're more complicated, or you can program a function to change all these values. But we're not going to get into that for now. That's a higher level of programming. So for now, all you have to do is that you can set the power to 1, or you can set the power to say -1 to strafe the robot, or 0 to stop the robot, etc., etc. And then this is the telemetry data. This doesn't really matter. So, but effectively, what this telemetry data does is that in the upper right hand corner, it is for when you actually program this. If you run the program, it'll actually be able to, in the top right corner, say is driving forward. Reset the field. And this is really important when you're debugging the code in real life, because it lets you understand what the robot's saying and what the robot's thinking and what the robot's reading. So then afterwards, you then set to sleep to 1.8 seconds. This is exactly the same as program the sleep here in milliseconds. Exact same code, except instead of the giant block, you just sleep the program for still the same amount of milliseconds. And then afterwards, you stop the car using exactly the same method as this program, which is set program, set power, front left, front right, back left, etc. All set to 0. Exact same as before. And we really see how simple, not so simple, how similar these two programs are. But of course, there are some major differences between them. Obviously, as previously mentioned, the reason why we don't use blocks typically is because there are a lot of opportunities for syntactical errors. For example, if I capitalize these words like power, or even if I undercase this like this, for example, just this, keep in mind, this thing has just simply lowercase the value. If you reset it and start the program, it'll immediately crash. And that's because programming is very picky if you do this with actual code. So there's a very high chance that you can simply mistype a number or mistype a word, and the entire program crashes, and you have to go through and fix it, and that takes a very long time. It's all very painful. And yeah, so when we translate and then also there are semicolons you need to incorporate, and you also, specifically for Java, they have these brackets and also these op modes. But if you are interested in learning more about Java specifically, I recommend you go through, and not just from this brief lesson, but actually go through an actual Java programming course, because I think that will be obviously the best for you to actually, if you really want to learn programming, to learn it that way formally from either school. They offer a lot of programs to learn these languages these days, or for a more formal programming class. But for the purposes of this is enough to program a robot, at least in the VRS. So we initialize the program, start the program, and works exactly the same as this. It goes forward, raises the flag. There. Everything's great. And so going back to the PowerPoint, here we can see all of these changes lined up side by side with each other. So front right direction equal to this. Power, time, same, and the power here. So again, we can really see how similar they are. So here's a fun little activity you can do using the Java code, is to go and make a move in a square. So this is just taking advantage of the previous movement commands you've learned. And, well, let's jump right into it. So sharing this. Now, in order to go and have more free space in order to play with, we will go over to, instead of these level selectors, which these are pre-made lesson challenges. They're great if you want to experiment and learn if you want to learn while programming and through fun activities. But more generally, if you just want to play around, you'll go to this programming page instead. This works exactly the same way as the previous one, but instead of, having this pre-made, arena of sorts with all the walls and you're a relatively clear direction with a goal and objective, instead you get this simulator, which is an open field, and you can, and it's pretty easy for you to just experiment with really whatever you want to experiment with. So, although there are multiple interpretations of doing this in Java, let's go over a couple of the easy ones. So let's see here, new program, Java program. Okay, so once again, let me just go back and copy and paste some of the sample code in the chat if you want to go and use it, because this makes things a lot easier. So let me just write example one. Nope. Fair to anyone with link. So let's see here. Here it is. Here's the chat. Here's the second link. So this is to get the code that we will copy and paste for now into the simulator. Make things easy on us. Oh, my bad. We first need that base code, and this is built off of that other code. My bad. Let me just go edit it. So okay. So let's see here. And again, you may copy and pasting code directly won't work. So give me a second to go and find the original code and just my internet's a little slow right now, so oh. That's it. All right. Well, okay, so here's the original code we do. In order to use this new code, you should copy and paste it into here, this op mode active bit. Copy and paste it from run blocks here. Within this section, just copy and paste. And of course, adjust the indentation. So indent it so that this lines up. So that looks like this. So this is the simple and kind of honestly pretty boring way of doing this with just two motors and just simply going at it. So here I'll show you what the code does. This is the pretty simple approach. You go forward, you rotate, you go forward, you rotate, you go forward, you rotate. Honestly, pretty boring, right? So let me teach you a more fun way of doing it, perhaps. Or again, using strafing. This is another reason why you would use strafing typically, is because unlike when you're really doing this, when you're rotating, there's a lot of chances for you to make an error while rotating. Strafing has a really great advantage in that it doesn't have that problem. There's no chance for it to ever go. There's very little chance that the strafing, when you strafe, right, it will not strafe exactly right, keeping the robot orientation the exact same. So this makes it a really powerful tool to use. And let me teach you how to do that. So with the code currently, it's you don't really. So currently with the code, what's happening is that it's setting the front left and front right power only. What we need to do is that we need to modify it so that it can use all of these programs. So front left, so front right, front left, back left, back right. And let's first see what this code does for now. So now we have these 4 different motors. They'll just move forward. Zooms forward very quick. Perhaps a little too quick. Go forward, zooms forward now. Great. Oops, too quick. But so here, initialize the program, you start it, it moves pretty quickly. So now we need to strafe this. So go forward, put in this code, and now we need to adjust these power levels. So again, please reference a chart. I really don't recommend you do the calculations about this in your head since it gets kind of horribly confusing after a while. So please take my advice, just don't bother to do this because charts make this so much easier on yourself. Just save yourself the pain in the chart. So here it is. It's the code to turn left. So code to turn strafe right. So now we go forward, and now you see exactly at a sharp 90-degree turn, it'll turn exactly right. And this is again one of the major great things about using mechanism wheels and strafing is that again, there's a lot less chance that the robot will say go this way, go perhaps angle upwards, angle downwards, left and right. Instead, it'll go exactly straight every single time. So afterwards, if you want to make it move backwards, you could either rotate it or, again, since the motors work exactly the same front and back, you can just simply do the cheeky option of simply you moonwalk backwards, or as I like to call it. So go forward, turn right, and now, hey, moves backwards. And then to complete the loop, you want to go and strafe the same way, but instead of strafing it forward, you instead strafe it this way. And this will let it strafe left instead of right by simply putting the opposite, by doing, I know it sounds a little silly, but just simply doing the opposite commands as the one that turned it right will turn it left. It's really simple sometimes. And now you move forward, and now, as you can see, it goes forward, turns right, goes back, and again, perfectly returns to the location every single time in a perfect square, unlike the previous option where if you really wanted to perfect it, you could simply make it by going forward and turning it, but it would require a lot of effort to go in there and manually adjust every single small bit of code. And really, it would get kind of complicated after a while. So, and so again, if you have any questions, feel free to ask me. And yeah. So I hope that you've so let's see here, application window. Okay, great. So again, this is the code. There are again many different interpretations. This one specifically here is for the one in the for the turning interpretation. But again, oh, how does strafing work exactly? Okay, well, first let me go and copy and paste this into the Google document. Make a square. So alrighty, so I'm glad you're curious about these things. Again, everyone feel free to ask any questions that they want. Well, no, I'm more. It's a great question. So here, let me go back to this. So let me go back to this diagram, and let's hope if I can explain a little clearer. So what's happening is that mechanism wheels are very special wheels. What they do is that they're actual wheels with little rollers on the side of it. Let me give you an actual image of one. Oh. Mechanism wheels. So I can show you what they actually, because this is again, mechanism wheels only work with this type of strafing only works with mechanism wheels. It doesn't work with, say, for example, a regular car tire. You're not, if you spin the two wheels on your car, they're not gonna strafe magically. I wouldn't recommend you try. Don't take it from me. But your robot will not have a. I mean, your car will not have a fun time if you try to turn the wheels in opposite directions. What the special thing about mechanism wheels are is that if I can go and get an image to load, dang it, mechanism wheels. Yeah, okay. So here's an image of a mechanism wheel for you. And these wheels are very special. As you can see, unlike regular wheels that you would have on your car, for example, these wheels are surrounded by smaller, longer wheels called with rollers. And these rollers are in an X shape. And what these X-shaped motors do is that if you set them up in a drivetrain such as this, they must form an X shape as shown in the diagram. And then assuming you set them up in an X shape, what will happen is that as you roll, say, for example, if you want strafe right, as you move this motor forward and as you move this motor backwards, these two forces will force the rollers to rotate in such a way that overall, the rollers are actually simply moving the robot to the right. Because how it's working is that if you get each of these individual wheels, individually, these wheels actually want to move in a sideways direction because of the rollers here. So these are not like, so if you just got this on a motor chassis, you got a single one of these, assuming you can somehow do that, and you got to rotate, you find that the wheel wouldn't go straight. It would turn for some reason. And that's due to these rollers. But the advantage of doing this is that if you get two of these motors and put them against each other in an actual drivetrain in this specific X shape, assuming you get all of these to move exactly with each other, not against the grain of sorts, the robot will move perfectly flat and the motion of these two motors, if they both rotate forward, will counteract each other, forcing the robot to move straight in one direction. And same thing with this. If you rotate this and this into opposite directions, what will instead happen is that the force cancellations of the mechanism wheels will cancel out. The forward and backwards motion will cancel out, and this will instead result in a net rightward direction. And same thing if you rotate it in reverse. Let's hope. Let's see if I can get you an actual diagram to explain the force cancellation behind between mechanism wheels. So okay, great. I think this is a pretty nice way to explain it. So here, as we can see here, the wheels by default don't actually move forwards when you rotate them forwards. When you rotate them forwards, they move actually to the side like this. It just so happens so that if you simply rotate both of these wheels in the same direction, the sideways moving bits cancel each other out, so the robot just ends up moving straight as a result. But if you don't move them together, what will happen is that if you studied physics, which I recommend you do if you want to really get a really nice and detailed definition understanding of this, is that you rotate against each other, the front and back parts of these arrows cancel out, and what happens instead is that they combine to go this up, down, and this arrow gets put up here to be a tip to tail. And so as a result, the net actual movement is to the right. And same thing for this side, but it actually, again, it's not the same as the left side. Instead, the reason why this side is the opposite is because these X shapes, again, force this motor to be in a completely different direction, forces it to go downwards, and this one to be upwards instead of this one to be downwards and this one to be upwards. So when they cancel out, again, though, what ends up happening is that if you attach these tip to tail, which is generally how you're doing this in physics, is that it will end up, this moves it down, but this moves it up, so ultimately it just ends up moving straight to the right. And I hope that, again, this is a kind of a simplified explanation of this, but this is basically what you need to understand here. It's, again, maybe a somewhat incomplete explanation of how mechanism wheels work, but again, I really recommend you go to perhaps do your own research, or if you understand physics, again, this will help make a lot of sense. But again, I hope this overall simplified, well, at least more in-depth explanation makes sense for now. Basically, what's happening in short is that you move the wheel forward. It's not actually moving the robot forward. It's moving the robot to the side. But if you get these two wheels to go against each other, they'll simply, this one pushes it to the side, and this one also pushes it to the side. If you get them to rotate against each other in a certain way, then the amount that this wheel goes forward by and the amount that this wheel goes backwards by are the same. So this will only cause the robot to move right as a result, since these are both facing right. And same logic with these two sides. And same logic if you were to say reverse these, what would happen is that this would go the opposite direction. The backwardsness of this motor and the forwardness of this motor would cancel out, and this would result in the robot going left. And I hope that really helps answer your question. Winston, yes. So going back to the slides. And we've reached the final part of the lesson so far. Oh, great. I'm glad that really helped you, Winston. So, okay, finally, let me just introduce who we are. We're team FTC team 2129. Our team name is Quality Control. We're based in Bellevue, Washington, and we're a community-led team. We are the 2023 World Champions, and we also have the 2023 and 2024 World Championship Innovative Awards. We also have 2024 State Champion, Alliance Captain, and also the 2024 World Championship finalists. And here's an image of who we are. This is our posing with our trophies after World Championship. And again, please go to the link in the please go to this link and subscribe to our YouTube channel where more lessons are posted, and we also post a bunch of other things. So again, I feel a little ironic doing this I guess it feels a little funny doing this, but again, as all the YouTubers say, like and subscribe. Please subscribe, and yeah, and this is our robot. I believe this is our World Championship robot that we won worlds with, and yeah, we're really proud of winning it. Are you going to share the slide? Oh yes. Here, let me go share the slides with you. I'm sorry, I didn't do this ahead of time. What? Share, copy link. Yes. Okay, so here are the links for the presentation. For the purposes of kind of scrambling down between our 1 hour and 30 minutes that we have together, there are some additional slides that have been posted that are in the actual slides. So again, if you want to find more examples, feel free to check them out. But yeah, let's see here. Back to the presentation. So again, feel free to, again, we're in Washington. If you have really any questions, feel free to contact any of our team members. We'll be really happy to help. We have a real great bunch of people here. And again, if you hope on starting out any of your own teams, or if you want more information on FTC, where you really just want more help, again, you can connect to us, or you can go in, is FTC the correct channel? What does FTC is the correct channel? Yes, FTC is the game we're talking about in this presentation. You have this here simulation. Yes. So, all right. First, let me just wrap this up, and then I'll be free to answer your questions in a Q&A session, so that we're not holding up everyone else. So, again, feel free to check us out. And again, feel free to ask us or really any of the other veteran teams in the Washington area, such as Sushi Squad, Robot Eclipse, High Definition. They're all really great people who are really happy to help mentor teams. And yeah, that's the formal conclusion of the PowerPoint. Again, they'll stay behind if you have any questions. I'll be glad to answer them. So yes, for this year's simulation, let me go find that for you. Let's see here. So here's the robot simulator for this year. Again, we have a robot simulator for every year, and keep in mind that this is still very much a work in progress. So here you go into the deep. So okay, I hope, and again, I'm sorry if I'm not pronouncing this correctly. Jaimini Shah. Yes, I hope this is really helping you. So okay,
Yes, thank you.
yes, great. And again, keep in mind this is still a work in progress, and we'll be sure to have a lot more features up and coming. But again, we only have a robot inserter and whatnot. So for tips for learning Java for the first time, well, Again, I'm sorry if I'm mispronouncing your name. Security.
Yes, actually, I am a mentor for FTC, but I just tried this simulator. But you don't have the this year fill, right? This year fill simulation.
This is the robot simulator for this year's game. It is Into the Deep.
Into the deep,
If you'd
but
like, I can show you.
do you have the same field? It's I didn't found our students were practicing, but it was the old field.
Oh, okay. Here, let me see. Okay, then. Full screen. Okay. I hope you can see the screen.
It was a
So,
previous year, and it's a couple of years back filled, not this year's.
I believe it should be updated, but okay, let me go see. Again, this is still very much a work in development, but so we go in and load it. And it should be a new one, although I'm sorry, the loading time is a little atrocious. The internet apparently doesn't seem to be acting up. Let's see here. At least it's in the robot arena on time. So if you go to single player and you go to Into the Deep and you start the game, and hopefully it's loading a little quicker on your end. And again, this is the exact same here in Robot Arena, which is programming page is just programming. Robot Arena lets you just simply control the robot and compete against each other in mock games. And they one of great things about Robot Arena. But assuming this field loads for you, and I hope it's loading faster for you than it is loading for me, it should actually load the new scene, and it should be the exact Into the Deep one, in order to let you practice. But so while that's loading, let me answer some other questions. So if you have any, so for learning Java, well, depending on your education level, I personally would recommend a couple of things. So first, if you have the opportunity to, obviously, I would recommend actually formally learning Java instead of through formally learning Java through perhaps if you have a school program that lets you learn Java, like here it seems to have loaded. Wait, okay. So here you go. This is really indeed the new field. If you can see, I can go forward, use this robot, etc. Go forward, practice with it. Move down. Yeah, move this robot in here back and right. I hope this is what it's showing for you as well. John Mini. But here's what the actual field looks like. Indeed, the field has actually been updated so that it is the modern field. Perhaps it was
Okay,
not there
I'll
in the
just check
past.
it. Thank you. I'll check it because previously my students were not seeing this field. It was a couple years back field, so I'll just check it. Yeah.
Yes. We do update these things regularly. So hopefully, maybe if there's an issue in the past, or also keep in mind though that we do also have previous games in the past. So be sure to actually click, because again, we have these ones: Sandbox, Center Stage, etc. Please click the one Into the Deep specifically, the Into the Deep logo specifically, and that will actually specifically load the Into the Deep field. Again, you can load other fields in these simulators. So
Can you,
again,
can you,
for
if you don't
yes.
mind, can you just send that link, this particular link of
Oh yeah, sure. Although it's the exact same link though, there's not a specific link for the page. But okay, sure. So here is for the programming page. Program. So here's for the programming link, and here is the link for the robot arena. I really hope that helps. So learning Java, in brief, I recommend learning Java through primarily your school or any other resources if your school provides them. I think learning through a teacher personally is the way I best learned it, and I think I really hope it'll work for you as well. There are a lot of great programs, such as, for example, again, reflecting how widespread it is. If you go to APCSA, which is a class I think most high schools offer it, you can actually, it teaches the class in Java, and you can also learn Java through it. if you can't find a teacher, which understandably not everyone has the opportunity and their high school does not have understandably that many resources. Again, we have again a lot of FTC members host a lot of these outreaches, and a lot of I suppose other people do so. If you have the opportunity to join one of those free online classes like this one, because we're just here to help people really pursue their passions in computer sciences or generally in STEM. Attend those as well because they will have more knowledgeable people who have actually worked with the code before. If you do have to, if you must resort and you don't have really any better options, I recommend checking out a textbook and then finally maybe YouTube. I would say textbooks are a little bit more reliable since they would have more vetted information than YouTube videos, which tend to generally be a little bit faster paced, I think, and not be as detailed as, at least personally, I would like it since the formal books have been published and have been screened for quality purposes, have been more generally screened for quality. And also, again, I generally personally, for me, don't prefer books or textbooks that much without a teacher present because I think it's real great to ask questions and really, if you have any questions, to really understand what you're learning. So let's see here. How can we try the joystick controller on the simulator? So, okay, so in order to try the joystick controller on the simulator, what you need to do is that you need to connect an actual controller to the simulator, such as Xbox controller or something like that, and plug it into your computer, and then you should actually be able to run it, I believe. Do you have program files to practice on the simulator? I believe if you go to new program, if you want to find some practice, okay, so for Java new practice files, okay. So if I'm sharing the correct screen, let me just be sure I'm sharing it. So share. Sharing the screen. Okay, so if you want to find new programs, the real easy way to do it, and just to try and figure out what the programs are, is if you can go new program, there are block programs. These will create several different basic programs for you to play around with, such as, for example, if I want to do tank drive, I can go over and it pulls up the program. And again, this also works for Java, which if you want to go do push block, for example, or something like that, it'll automatically put in the code for that. And I think this is a real great way if you want to really see what the code should look like, or if you want to get basic bearing on it. Okay, so now Calvin, what's your question? I'm sorry I made you wait for so long.
How do you get to this thing by yourself?
I'm sorry?
How do you get to this thing yourself?
Get to the what?
This thingy yourself.
Oh, the simulator. Okay. So the simulator we used in today's lesson was the Ultimate Goal Simulator. This is the one that's been specifically made for more teaching purposes. So here I posted in the chat. It's https www virtual robot VR robot vrobot sim .online/homepage.html. If you wanted to check out the Into the Deep one, it is if you want to check out Into the Deep, this one, Into the Deep. Yep. And yeah, and these are the two, simulators shown again. But again, if you want to check out the rest of the simulators, go to the website as I previously said. And yeah, if you go to the website, we will have a lot, such as a virtual robot simulator. Go to Get VRS, and you can check out all our different virtual robot simulators, which are currently we have 4 of them, and this one's a robot importer, which not quite the same thing, but yeah. Virtual FTC sim. What okay. How is FTC similar or different? And I hope that answered your question, Calvin. If it didn't, please tell me.
Yes, this question I can answer. This VR simulator is different, and FTC sim is created by Canada, so that is a different simulator. That is also pretty good. My students have tried that too.
I see. Thank you.
Again, if you're any other questions, feel free to say them. This is just the question session, and I'll be sure to get to you. again, I think the major difference between this is that I believe FTC Sim is not made by the community instead, and Virtual Robot Simulator is, again, it's headed by a team in Illinois, but really like I think a lot of FTC members from all over. Really, you can take a look at the About Us page, our team page, but really it's all made by community, made by a lot of FTC people to really provide the real FTC experience. To really provide so again, FTC Sim again is another great option to use. For our purposes, Virtual Robot Simulator, it is free, it is easy to use, and it is also I think a little less directed than perhaps FTC Sim, which they have more oriented lessons as you can see here compared to ours, which is more just we give you the field and you really
And
spend.
also they can create a student's profile and also the teacher's profile. And if there is a teacher's account, they can add the students. They have such sort of ways to do.
Yes. Are there any questions? Again, if you're really any concerns or anything you aren't aware of, please feel free to ask me. Um, again, this is really your time. There's really no bad questions to ask here. Again, I'm aware I may have gone over some of this information somewhat quickly for and to help cram in a lot of information. Or if we start Android Studio, can Android Studio be transformed to block code by copy and paste? Okay, so that's a great question. Unfortunately, I don't believe Android Studio code can be transformed to block code by simply copy and pasting it. There is no automatic way to transform Java to block code. I believe actually transforming block to Java code is a lot easier, but I don't believe that's possible through some automatic program either. It's either you program in Java or you program in blocks, unfortunately. I'm sorry. It's because in Java, you have access to a lot of different programs and packages that simply are not programmed in blocks. So, for example, in one of our cases, we use a program called a Roadrunner, which allows us to basically smoothly move our robot in a specific defined path throughout the field. This is real great. This is real great. It has a lot of fancy curves and whatnot, but actually representing this code though in blocks is almost impossible since it builds off of a lot of different programs and a bunch of other features and functions that I mean, if you were to program this in blocks, it would probably crash the program due to how long it would be. So, again, unfortunately, the basic answer is no. Yeah. Do you have the guide link for the VRS? Okay. Yes. So for the VRS website, so again, here's the VRS website, and here's the guidebook. And again, I really recommend checking out the guidebook if you like to go and learn more. Oh, okay. If I can I just use the encoder no dead wheels? Okay, so first of all, Johnny, for the so for the Roadrunner question, I believe technically you could simply use the drive encoder, but I don't really recommend it since they're not meant for precision purposes. How the encoders work is that if the robot spins, it simply tells the robot motor that it's spinning, but it doesn't actually reflect how the robot actually moved at all. So it's kind of a moot point whereby technically, but say for example, your robot is just simply hit a wall and the robots are randomly spinning. The encoder will still record the robot moving forward, even though the robot is not physically moving against the wall. And that's the reason why you typically include dead wheels, so that if it does hit a wall, it doesn't the dead wheels won't spin, but the actual encoders will still record the motors as spinning. So this will let you know that it's actually not working correctly to prevent any of those situations. Again, okay, this is outside the scope of the actual presentation, but again, this is just for when you're actually doing FTC.
Because
Unfortunately,
this is our first year trying the Roadrunner 1.0, and we have never used the dead wheels though previous, but this time we are trying to use a Roadrunner with driver encoder. It's precise. It's not too precise, but it works fine.
If you have any questions or if you need help with that, feel free to contact our team. Actually, we will be happy to provide any guidance or any help to you because to provide any help. Again, we can go over or we can go online and we can really help you learn the in and outs of Roadrunner. It took us a long time as well to get it because we got it from another team that they mentored us in turn. So
I
again,
see.
yeah, again, feel free to communicate with us. We're more than happy to help your team if you want any help with setting up Roadrunner for the first time. And again, I
Yeah,
think you're
it's for the first time, and right now we are not using dad wheels, but we would be trying to use the dad wheel in future. Like supposing we can use in second game, but in first game, let's see how the Roadrunner with driver encoder works.
Yes. Again, I don't really recommend you using coders for Roadrunner. There's a reason why data wheels are typically used. It's because encoders are not kind of miss the accuracy point of it because encoders will still record the robot as turning even if the robot's not actually turning. Encoders don't function exactly the same as dead wheels. So
I see.
yeah,
Okay.
I mean, again, though, if you want a more complicated guide, again, feel free to contact our team. We'll be more happy to provide mentorship or really just general guidance if you have any questions using it, because we've been doing this for quite a while now. And
Oh, I see. Can I have the contact of your team?
oh yes, let me go pull that up. I don't remember off the top of my head. Um, let's see here. So.
And by the way, what do you recommend? Two dad wheels or three dad wheels? Like
I
two
suppose
dad
it really
wheel.
depends. Personally, I think it really depends on the purpose of what you need it for. Generally, 2 dead wheels is good enough, but 3 dead wheels is best for if you want that high precision tasks. If you really want something to be extremely precise.
Because
But
this year into the deep, I don't think so. We require any like there's no randomization, so we don't require any webcam or any kind of the vision processing.
yeah, basically, what I'm trying to say here is that basically, how it basically is that if you have 2 wheels, okay, that's good enough for Roadrunner. Pretty much, that'll provide all the information you really need. If you have 3 dead wheels, that provides one level of redundancy, which is nice to have because
So which is easy to program, like two dead wheels or three dead wheels?
I believe 2 dead wheels is generally easier to program, but I mean it's not really that much more complicated, I believe. It's not like League's more complicated to program with 3. It's mainly just a engineering thing where how many levels of redundancy do you want? Because again, there's a possibility that simply the 2 dead wheels, I mean, they may work fine all the time, except for that one time where maybe one dead wheel falls apart, where maybe, I don't know, the dead wheel just doesn't do its job properly and spins
Because
off
I
randomly.
see lots of messages in, I am a member of FTC Discord. In that, I get lots of information of the Roadrunner. I see lots of messages and errors for the three dead wheels, two dead wheels. So also, yeah.
Oh, of course. It's very difficult. Setting up Roadrunner is again pretty complicated. Understandably, there's a lot of errors for this. Again, if you want to learn how to set it up properly, feel free to contact us. Um, but again, it's obviously there will be a lot of errors when programming this initially. Our team personally has a lot of errors as well. Debugging though is a very natural part of the process, and don't be discouraged just because there's some errors and that occur. This is very just keep in mind this is very natural, and even our team, which is at least I would like to think we are a very top level team, even we struggle a lot, and we have to spend a lot of hours debugging our own programs as well. So
Yeah, sure. That's how you learn, right? If you don't get error,
yes,
you
yes, yes,
can't
of
learn
course.
anything. And by the way, how does the Meep visualization work with this Roadrunner FTC dashboard? Do you need a Meep also for that?
I feel that
Or
this uh, I feel that it probably would be easier again to just contact our team at this rate and just again, please just feel free to contact our team. I think it'll be much more effective if you want to go through like an actual video chat session or something more specific with
okay.
perhaps one of our, yeah, with somebody who can explain to you so in so much more clear. Also Roadrunner, unfortunately Roadrunner, even though I give an example, it does not actually have an ability to do work in the simulator, I don't believe, because we are still in development, but
But still, we have that Meep. It can work in Meep, right? Roadrunner.
um meet. I'm sorry, I don't know off the top of my head.
It's a motion planning lab. It is by the Roadrunner. I don't know. It's
No,
built.
I
You
believe
need to it's at the GitHub, and you need to download the and on the Android Studio, and then you get the same fill like, and you can just visualize. You can have the
yeah, no,
path and the robot moves.
it should work, yes. But again, though, it's complicated to set up most of these things. Roadrunner, again, I wouldn't recommend any beginners at any rate actually go in and try to do this. Just again, Roadrunner is a very advanced program. Again, it does provide a lot of that necessary speed ups in time in movement. That again, a lot that's really important if you really want to hit the top level. And I understand, but again, though, Roadrunner is very much a collaboration of both the programming and robotics aspect of the robot. So it is best to go and have to do this like maybe in person or maybe with some more visuals and trying to briefly go over this with in a group chat session. I'm sorry if that answer is not satisfactory to you. But here let me go give you our FTC 21229. Again, though, please feel free to go and here's the Gmail for our team, ftc21229@gmail.com. And I'll also go and share with you a Discord link because if you want more immediate help, let's see here, FTC and friends. What's the so? And then we also have a Discord channel if you're a coach or something like that. Yeah, and this is quality control, and again, we have a lot of different teams working with us. So if you want to join the Discord channel, please, you'll be much more active there. But we also have the Gmail as well. We also have Gmail if you want to add it. And yeah, again, I'm sorry that I can't cover the entirety of how to use Roadrunner in this relatively beginner level and present out lesson. But again, if you really want help,
Thank you so much for
yeah,
your effort to
yeah,
explain
yeah.
and give this email and Discord. It will be very helpful
Sonia?
to us, our team.
Yes. Again, please don't feel afraid to ask any questions. And also, again, feel free to reach out and really email our team members. We're more than happy to help. And again, do
Okay.
you have a question? Um,
Oh, my bad. I didn't know I was unmuted.
no, don't worry about it. This is this is already running significantly over. Again, the meeting is really over. So again, it's really if you want to take a look at it, but let's again, if you feel again, don't feel any problems at all. So so the Milan is just it's a simulator thing that lets you visualize the Roadrunner. It's yeah. We have the programs and but again, we're more than happy to show you how we do it here. But if you collaborate there, if you want to communicate in some more dedicated session to this, but for now, I don't want to go too crazily deep into how Roadrunner works and how to set that up on the robots, and that's extremely beyond the scope of this kind at this rate. But does anyone else have any other questions? Well, if no one else will have any questions, again, thank you for attending this lesson. Thank you for attending this Q&A. And again, I really wish you the best. If you have any questions, feel free to save the Gmail or save the Discord channel. We will be free to answer any questions you have. We check them quite regularly, so you know, I definitely will get back to you as soon as we can. And yeah, again, really thank you all for attending my lesson here. I hope it really let you get a good understanding of at least the basics of blocks and Java programming. And I hope you can really take this information and again, if you want to pursue STEM in your life, really go in, find more resources, go take some classes at your local school, or again, attend more workshops or outreaches or things like that. But overall, have a great day. And again, thank you all.
Thank you.
Bye.